on here, okay? But I want to make sure we understand what's going on with this. Whoops, Daisy, didn't want to do that. Let's go back to edit. I really don't want to do that. So, but let's talk down here. I'll just bring this thing up and look at it. All right, hold on a second here. I don't want to save. I'll cancel this. All right, so when I bring this thing up, I'll bring it up a little bit bigger for you so you know what we're talking about here, okay? Now, we're talking about fits are going to be basically in 3 different categories, and this is what we learned about when we talked through the handbook. They're going to be 3 different ways. Either they're going to be what we call running or sliding clearance fits. That means this. That means that the largest shaft, when it's dimensioned in the tolerances, the largest shaft is still smaller than the smallest hole, okay? Which means that it can go into and out of this without any type of interference. That makes sense? It's called clearance or sliding. Yes?
I got scrunched.
Already? Austin, you are nothing if not an overachiever. So well done. Thank you so much. Normally it's Emily. Emily, you've been trumped today. How about that? All right. It's just a matter of time for you, Emily, okay? So understand that. So the first type of clearance fit is something called an RC, or running clearance, okay? It's a good way to remember that. And it means that the largest shaft that we have will still be smaller than the smallest hole. No matter what I put that thing inside of there, it's not going to hit. It's going to come right back out again. All right. The other extreme is something called a force fit, or an FN. And what that means is no matter how big the hole is, the largest shaft will always still interfere with it. Which means that if I want to put those 2 parts together, I'm going to have to force that thing inside there. Now, is it going to come back out easily? Absolutely not. Okay? Hence the word force. And it's going to be something that's beaten together, but it will stay that way forever. Okay? It's very hard to separate a force fit.
Did you say the largest shaft is?
The smallest shaft is still larger than the largest hole. Okay? So you got the extremes on there. So the smallest shaft is still going to be bigger than the largest hole. Whereas the clearance fit, the biggest shaft is still smaller than the smallest hole. So we're going to be interfering on that one. So clearance is always going to slide in and out. And the force fit inside there is always going to be, no matter what the tolerances are, the smallest shaft is still going to be bigger than the biggest hole. So it's going to always stick. Now, what happens between those 2 extremes is shades of gray. And that's what you're seeing with the LC, the LT, and the LN. Typically, it's just going to be that LT in the middle inside there. And what that means is, when I tolerance this thing, it's a real possibility that the biggest hole may be bigger than the biggest shaft, which means it'll clear, okay? Or conversely, the smaller hole is going to be smaller than the smallest shaft, and it will be a force. But again, based upon whatever the tolerances were by the engineer who created this, they're going to get that situation. What that means is whoever makes this, and they're within those tolerances, it will do what the designer intended. It will always miss, it will always hit, or depending on the variance that you make when you actually create the part, it could clear or it could interfere. Okay, it's either and either or both. Does that make sense? Very odd, okay? But nonetheless, this is the concept I'm trying to get across to you. Now, what does that mean for you? Well, what you see on here is a series of mating parts, a shaft and a hole. What I'm going to be giving you is information about them. I'm going to say, okay, so for this particular part right here, we know that the diameter of this piece right here is going to be a certain value. Now, what I suggest you do on all these is to start this way. Start on the dimension layer and do these individually. Do them individually. So I'm going to say, all right, I'm going to go ahead and dimension this part right here. And there's the size of the shaft, okay? There's right there. And the size of the hole over here should match it at that same 0.570. Everybody agree with that? Now, let's get back and take a look at our instructions real quick on here, because the instructions are very important. They say here, from the tolerance charts given on the following pages regarding class of fit, determine the solution for all of them and the tolerances requested for each part. Remember that larger of every pair of tolerance values is always listed first, and provide all answers to the nearest 10,000. That's 0.0000. So I want you to start by taking every one of these examples and taking the precision automatically to 4 places. Every one of these, take them out to 4 places, like so, okay? So now we got the right precision on here. Now, I want you to dimension each hole and each shaft using the associated fit tolerance that's given to you and has to be calculated, Lane. Okay. So I'm going to demonstrate exactly how to read the charts. I'm going to demonstrate exactly how you have to answer them and then display them. But again, my first biggest piece of advice on you is do them one at a time. One at a time. Don't look ahead, don't look behind, do one at a time on here. So, I'm going to be honest with you, dead level honest on this one. People either knock this one out of the park with 100% and they get a great grade on it, or they fail this miserably. And the reason they fail is because A, they're not paying attention, or B, they don't believe what I say and they go do what they want to do anyway. Does that make sense? Pay attention, take good notes, happiness is yours. This is one of the easiest assignments you'll do this entire class. Easiest assignment to do, the entire class. Every one of you could be done with this within an hour, okay? Let alone take the second day on Wednesday. But that's fine. Pay attention and believe what I have to tell you and do it the way I tell you, and you will be fine. So far, so good. You've dimensioned these two guys to determine, and look at that, it matches the dimension we said for the nominal diameter. Okay, cool. Now it says that here the class of fit is something called an RC3. So just based upon what we've learned so far, we know this is going to be a clearance fit, right? What that means is, in our minds, we know that the largest shaft is still going to be smaller than the smallest hole, okay? So it's going to go into and out of this thing. Does that make a difference over here? Well, if you kind of keep it in perspective, it'll help you keep things clean. So what is it you're expected to do? All right, so given that classification of fit, I said back here on the assignment, you'll see that I took all these pages out of that handbook. And here I've got a page of RC fits. The next one I've got a page of LC fits. The next page I've got a series of LT fits. The next one I've got a series of LN fits. And then the last one back here is a series of FN fits. So I've gone from clearances all the way to pure interference. All right? Now you can look these up in your handbook the same as I'm doing right here. I have no problem with that. But I'm giving you these charts if you want to refer to them. So what does this mean for us? All right. I've got an example problem back here I'm going to do as a demo for you. Now the demo back here, you see in this case, I've got something here, and I've said that this guy's an RC1 fit. Yes? Okay. I've got an RC1 fit, and we're going to grab, make sure we get Kale in 3, 2, 1. Got you, Kale? All right. So let's work on this together. Now I have down here in my possession actual RC1 fit right here. This is my table. So this is how you're going to read this. Once I get this thing dimensioned that you see on there, once I get it dimensioned, you're going to come back through the chart and you're going to find the chart that matches it. RC1, I found RC1. Everybody with me so far? And you've got all these charts. The next thing I must do is this. I must determine the nominal size range for this particular part. And you'll see on here, this is at 0.5500. And I look on here and I say that 0.40 to 0.71, does this fall inside of that range? Yes, it does. That's why I've circled it up. Now, you'll notice directly next to that, there's these series of pairs of numbers that you can see right there. Now, this is where people get confused. They'll read the wrong lines. Okay, and that's why I've circled it up over here. So I've said, okay, great. Now, and if you want to do this, I have no problem with it. You want to print off my charts, print them off the printer over there, grab a highlighter, say, okay, I highlight the RC1, I highlight the range that I'm supposed to be inside there, and I'm going to highlight those 6 numbers you see that I've circled on there. I need to use these numbers for my filthy purposes in order to answer the question about its limits for the shaft, the limits for the hole, and something you call limits of clearance or interference. It's going to be one of the two, okay? Or both, depending on the fit. So let's explain what you have to do. So let's start with the hole, okay? It's listed first right here. I follow that hole information and I find 2 numbers down there. See those 2 numbers right there? What these are saying to me is this. If I'm going to tolerance this and you're going to tolerance fit this right here, when I come back here to my dimension style manager, I'll slide that over to the side. When I come back here to my dimension style manager, and I come back here and I'm going to do an override, for the love of God, don't do a modify. Okay, again, do these each individually and do them as an override. I will come back here to my tolerances. And we're going to change all of our tolerances to limits tolerances. You all know how to do this. But remember, 4 place decimal. Imperative. That's what it says in the instructions. The answers have to be to 4 places. All right, so what do I do next? I'm going to do this for the whole. Well, what this is over here is I'm going to add plus 0.3 to the top number up here, and I'm going to subtract 0 from that top of the bottom number. Well, if you ask yourself, does that make any sense to add 3/10 of an inch to this thing? 3/10 of an inch, that's almost 1/3 of an inch. So here's the first thing you must know and you must recognize and do, and that is this. When it says for that top number, plus 0.3, what it's really saying is, for the sake of printing over here, the chart moves. It moves 3 decimal places, 1, 2, 3, to right there. There's my decimal places. So instead of being 0.3, it's 0.0003. Everybody understand that? I'm moving that decimal place 3 places every time. Well, that makes perfect sense now because we're doing everything in 4-place decimal. Does that make sense? You have to do that every time. Move it 3 decimal places. Okay, what about the one below that says 0? It doesn't matter if I move the decimal place 4 places, 0 is always 0, right? But remember what we learned in doing dimensioning on here with our limits tolerances on here. What the first number is, that 0.0003, is what's going to be added to that top number. I'm adding that value to the whole to make it that much bigger. To the bottom number, it stays exactly the same. It's 0.0000. I didn't add to or subtract from it. Now remember, these do a mathematical equation. This adds to the number, this subtracts from the number. Now I've got what I want. Limits tolerance, 4 places, added 0.0003, added 0, I click OK. Now what I can do is I can either redimension it or I'll do a dimension update, and it reflects those 2 values. Make sense? All right, now let's do the same thing, but for the whole. So when we look at the whole over here, I'm sorry, for the shaft, right, for the shaft. The shaft says minus 0.0 or 0.25, okay, and minus 0.45. All right, so again, I'll write these down up here. Minus 0.25 and minus 0.45. Did I get them right? Is that what it says? Lane, thank you. All right. So again, what does this mean? Forget the minus on there for now. I'm going to move this 3 decimal places to right there. 0.00025. Now, what's wrong with my number? It's 5 decimal places. And we know it has to be to 3 decimal places. So if you have a 5 or higher, we round up. So 25 becomes 3. Does that make sense? And if it's down here, I'll put that negative out there. 1, 2, 3 places to right there. 0.0045 becomes what?
5.
5. See what I mean by that? So you have to do a little bit of extracting and extrapolating here. So notice that both of these say minus in front of them. What that means is, for the size of the shaft, in order to make it a clearance fit, it has to be smaller than the hole. That's why we both have minuses in front of there. Now, you say, okay, well that's fine. Let's come back here to our Dimension Style Manager. And we're going to come back here to, again, override. Come back here to our tolerances and change that to 4 places. That should be automatic, bang, bang. Okay? Now, from looking at what we just decided up there, we know that this adds, this subtracts, right? We know that. This adds 0.00007, and this subtracts. Well, the problem is this. This one's easy, 0.0005. That's easy. I know it's going to subtract that value from it. I don't even have to put a figure inside there. I don't put a minus sign in front of it. But the other number is going to automatically add 0.0003, and that's going to make that shaft bigger on top, is it not? So what we have to do in order to make this one a negative number is we have to add a negative 0.0003. Everybody see what I've done right there? Okay. Now, so you see what I did? I put that minus sign in front of there. So it's adding a negative number. So it's going to make that number smaller then. This one's automatically subtracting. Don't put a negative in front of that, or what's it going to do?
It's going to positive.
It's going to be positive. A double negative is a positive, right? So this is something you got to pay attention to. Like I said, you pay attention to this and you respect everything about this, you're going to fly through this and be brilliantly aid, okay? You don't pay attention to it, you're going to fail and crash and burn miserably. And I'm trying to help you with this, so you're paying attention. So I'm going to go ahead and close this. And now when I go and do that dimension update on this one, I see that I've got this. So it took 0.0003 away and took 0.0005 away. You with me? All right, so how do I solve the rest of this problem? Now, right here, on this problem right here, yes?
Scrunch.
Okay. All right, easy enough, Ray. 3, 2, 1, you should be back. We got you? All right. Now, what I need to answer down here. So I've now solved these two problems. I've dimensioned them according to the class of fit and what I learned for that particular category. Not so hard, is it? Down here, I'm going to answer some questions. So starting there with shaft limits, you will notice that back here in my instructions, and this is where I can't stress it strong enough. The instructions say, whenever I express these answers, here it is right here, come on, here's right there. Okay? Okay, the larger of each pair of tolerances value is listed first. So when I have to answer this question down here, I'm going to come down to shaft limits. I'm going to double click on this. And the shaft limits on there is going to be, here, shaft limits, click, there it is. Blinking cursor, come on. Click, there we go. All right, so blinking cursor moves down there to the end. See the blinking cursor, everybody? I'm going to add to that note. And I'm going to say the shaft limits are, in this case, 0.5497 slash 0.5495. Now, that answer is right for two reasons. One, I put the exact same values I had up there in my dimension up above. Agreed? Two, I listed the larger of the two numbers first. Does everybody understand what I mean when I say that? 0.5497 is bigger than 0.5495. Hence, when I list them, 0.5497 is listed first, slash 0.5495 is listed smaller second. Another place where students miss points frantically, and I don't understand why. Top number, always bigger, bottom number always smaller, bigger number listed first, smaller number listed second. Everybody understand what I'm asking for there? Okay. Now, whole limits. Move that cursor down there to the end. And the whole limits will be expressed as 0.5503 slash 0.5500. Did I list that properly? Yes. Larger number was on top, larger number is listed first. Smaller number on the bottom, smaller number listed second. So far, I am correct, showing the exact same information down here as I show up there. Seems pretty simple, right, Ray? Right? Okay. Now, next question is something called limits of clearance. And the limits of clearance is this. If I look back here at my chart, this last one I put down is called limits of clearance. It says 0.25 and 0.75. Well, we know because of the way we list these, 0.25 and 0.75 is really what? Okay, 0.0003, right? And 0.0008. Everybody see where I got that from? Okay, I can't have 5 places, so we got to round that 7.5 to an 8. I've got to round the 2.5 to a 3. So I will write that on here. I'll come down here, I'll say, okay, great. I'll come down to here, move that cursor down there, and I will list them. Which one's first?
The largest one.
0.0008 slash 0.0003. Okay? So that's what I get for my answer there. And that's based upon this chart right here. Now, what does that mean? What does this mean? That means that when I'm doing this on here, the clearance between the smallest shaft and the largest hole will be how much? What's the difference between that number and that number right there?
.00075.
What is it really, Ray, for our purposes here?
.0008.
8, okay? What's that number down there? 0.0008, okay? What is the difference between the largest shaft and the smallest hole? Say it, Lane, nice and loud. 0.0003. What number did I get down here, Lane? 0.0003. So you see what I'm getting at here? This right here is your answer to the differences between these. And if you think about it in this term, like I said, the largest hole and the smallest shaft has the difference between 0.0008. And the difference between the smallest hole and the largest shaft has a difference of 0.0003. So I can police myself. I can look at these two numbers and say, 0.3 and 0.8. And those should be the answers I have down here. And it should be the difference between that and this and that and that. Make sense? If those numbers don't match, you've done something we call wrong. You may not have heard this much in your life, but you're going to hear it now.
I'm married. I hear it every day.
That's daily for you, right? No matter if you're right or not, it doesn't matter. You just assume you're wrong and go on, right?
Works
What
for
I've
me.
discovered, and let this be a lesson for all of you, is if you know you're right and they're wrong, okay, let them prove themselves wrong.
Yeah.
Let them go ahead and just do that. Just let them prove themselves wrong, okay? Don't ever say I told you so, okay? But just somebody come back later and say, hey, I've got an idea. Let's try it a different way, okay? And see if that doesn't work better. Now, you've been married for a while, right, Austin?
Yeah.
How long?
5 years.
5 years, okay.
Lucky.
Okay. My wife and I have been together for 45 years, okay? 45, that's a long time.
Yeah.
I've learned some stuff, okay? But you'd last a long time that way. How long have you been married, Lane? 3 years, okay. All right. So you learned too, haven't you? Yes, you have. Okay, so this is what you're going to do, folks, on every single problem inside here. Now, I'm going to talk to you about a couple of other little small pitfalls that you're going to pay attention to. First of all, again, you have, yes. Okay, let's get you taken care of. It won't take much longer. I've only got just a couple minutes worth of information left to talk to you about it here. 3, 2, 1, okay? Now, on examples like, let me get this out of the way here too. All right, down here on this guy right here, you're going to see something happen for this particular fit. And I'm going to bring it up here a little bigger for you to see this right here. All right, so on here, again, pay attention to the plus and the plus. So plus and the plus. So you see that shaft is going to get bigger so as to cause that interference. So when you do this, make sure for the top one, you don't have to change anything inside your Dimension Style Manager. Back in Dimension Style Manager, here we go. On this guy, override. So when I get back here to my Dimension Style Manager back here, all I have to do is just go ahead and type in that regular number. No minus up there at all. Okay? Just going to backspace it there. So I'm going to add 0.0008. The other one below it says 0.0005, but it's also an addition. This is where I would make that double negative. A double negative gives me a positive. So I would add to that bottom number instead of subtracting from it. Does that make sense? The only other thing on here to pay attention is this. For instance, and this is not particularly on the problem I'm going to be teaching you, but I want to show you this. See this one here? It says 1.2? 1.2. All right, what that means is this. If I have 1.2, I'm still moving the 1, 2, 3 places to the right. 0.0012 is your answer. Does that make sense? That's how we actually get the thousandths instead of the 10,000ths. So if I ever see a whole number, the 1.2, whatever it may be, we're still moving that decimal place 1, 2, 3 places. It just means we're going to have 0 and 0 in front of it, so it becomes 0012. That's why. That's the only difference. We still move that decimal place 3 to the left. It just happens that that 1 is moving the place where we used to have a 0. So I want to make sure you understand that. So the only other pitfall on here, happens back here on the last problem. So here are your problems you have to do. On this last problem, you'll see on here that I've got a rectangular hole and I've got a rectangular shaft. And I'm giving you an X dimension for the hole, I'm giving you an X dimension for the shaft. What I need you to do is treat these like you did all the other ones over here. You're basically doing two things on this one problem. Does that make sense? two things on the one problem. So instead of here, what you'll do is you'll actually have a linear dimension on here, 4 decimal places from there to there, okay? And that is now your x. I'll make that up there to 4 decimal places, right there. I will kick it outside so you can read it, okay? So this is gonna be a limits tolerance for that will be my whole dimension for that value in my chart. This over here will be the, come here, the shaft value from there to there is my shaft value, and okay, there it is right there, and then again to 4 decimal places like so. So that's my whole, I don't know why I erased it, sorry about that, and this is my shaft. So I'm gonna have to answer those questions. I got you, Daniel. Daniel got scrunched, so I'm gonna take care of that. And we're right in the stretch. We're at the very end of the lecture here. 3, 2, 1, and you're back, okay? So I've got the shaft distance here of that value. There's the hole distance. So answer it down here. There's my shaft x, okay? There's my hole x. Then I'll do the same thing for my shaft y and my hole y. I'll get them down here. So that's what the values are they're given outside here. Now notice I don't ask you for that last value of the tolerance on there, the limits of clearance. Now, notice that last question, limits of clearance. That is how much it actually clears. That's how much it actually clears. Interference, same answer. Okay, whatever I get for one answer or the other answer or there, it's just we're going to call it limits of interference. This was also limits of interference. But this guy down here is a transitional fit. See where it's an LT, it's a transitional. That means I'm going to have clearance of a certain value and an interference of another value. How do I get that? How do I distinguish between the two? Well, as I said before, the smallest shaft and the biggest hole will be my clearance. But my smallest hole and my largest shaft might be an interference. So all I need is one 4-place decimal number here, another 4-place decimal number there. Now typically, if I had something like this, it would actually be listed as like 0.0006 / minus 0.0007, and that minus would indicate an interference. That makes sense? So, but I broke it out to 2 separate answers here, just so we can distinguish between the two. You don't need to put a minus sign in front of either one. We never have to call out positives, and there will be no positive or negatives for these answers at all. Just whatever the clearance was between the smallest shaft and the biggest hole, it'll clear. And this one, the largest shaft and the smallest hole is probably going to interfere, and you just need to give me those 2 numbers inside there. That's where it ends up. And then limits of interference, you're going to get always list the biggest number first. Limits of clearance right here, always the biggest number first. And I don't even ask you for that limits of clearance or interference on this last one. Just do this guy twice and give me those answers on it. So you can understand, it's not a difficult assignment. It's really not. Not to impugn any of you, it's really not that difficult. All you really need to do is you have to pay attention. You rush this, you fail this. You don't heed what I've taught you, you fail this. You slap your way through this thing and don't care, you fail this. However, you do everything I told you to do, you do the simple process of everything I told you to do on here, easy A, easily done today. Now, as many of you have become accustomed, many of you will come up to me and drop it in my lap and say, hey, did I do this right? Okay? I will still be glad to answer that question for you. But what you're going to do is you'll hand me your print, and I'm only going to circle the things that are wrong on your drawing. And you need to go back and you need to figure out what you did wrong to do it. I'm not going to say, oh, the answer to that was 0.005, and you put 0.006. That's not how it's going to work. Okay? I'm not giving you the store on this one. On this one, you hand it to me. I will circle up the things that are wrong without you standing there, because I'll have the answer right in front of me, okay? And I'm going to bring it to you and I say, okay, these are wrong, that's wrong, and this is wrong. You go back and you figure it out. If you get stuck, I'm not abandoning you, okay? Hey, Doug, I'm sorry. I've beaten on this 4 times already. I still can't give you a different number. What am I doing wrong? Okay? Most often what happens where people are wrong, and this is going to be funny, but they choose the wrong classification. Or they find the wrong place for their dimension between those limits. You see what I mean on that one? I had to be between 0.4 and 0.56, and if I'm at 0.57, I'm in a whole different category. You understand what I'm saying there? So pay attention to where you choose on here. All right, and then they'll say, well, wait a minute, now, the number I got here didn't match with what I got over there. Well, did you make that a double negative to make it a positive? Oh, yeah, that's right. So don't just sit here and drone your way through this thing. Pay attention. Somebody's gonna wanna know how you know how to do this, and this is how we do it. So, you want me to review it? Glad to. You're just not gonna peer over my shoulder, and I will tell you what's wrong. You go back and fix it until it's right. Hence, the perfect score. No problem with me. It's still on you to figure it out. So hopefully you paid good attention, you understand what I'm asking of you, and you understand the whole process of what gets rounded and what, how we change double negatives to positive, how we subtract from that top number instead of adding to it by adding the minus sign. And the rest of it is cake. And you like cake. I like cake too, okay? All right, any questions from anybody? Yes, go ahead, Kale.
Does the whole always get the nominal value?
They both get the nominal value.
But like the whole's always, like it looks like
They're
they always get the
both always
zero.
starting out with that nominal value.
Right.
They
but-
baseline, both the hole and the shaft are always gonna get that nominal value.
It's-
So that's why I say to you, come back here, the first thing you do on every one of these is to go and throw the dimension on there and make sure that when I put that thing to 4 decimal places on here, that it matches what you see down there. Does that answer your question?
Kind of. It's more on the limits of each one. The whole gets a 0.
Oh, what he's asking for is over here. When he's looking at the chart, is that what you're asking there?
Yeah, on the.
Then whatever
whole
the
value.
size of that object is, that 0.7125, is I'm gonna find it right inside here, so there it is, falls inside that category right there. Does that make sense? Does that answer your question or not? Still not?
That was just for standard reasons. Does the whole, because the limit, it looks like all the holes get 0 as one of the limits.
Not always.
Oh, not
No,
always.
it happens with this guy right here. Well, not even on here. There are some zeros on there. But this is a wonky chart, okay? And I have no idea what the rationale was for doing this one, but somebody somewhere hundreds of years ago sat down and standardized all of this stuff, and that's how it made it inside here. So, no, don't ever assume anything. You look at that chart and you circle up the area you're supposed to be in.
Okay.
And yeah, maybe it's a -0, maybe it's not. So don't ever make any assumption like that. You go look it up, you find out exactly what it is, and you apply it. Yeah, I understand your question now is, no, the most dangerous thing you can do in here is make an assumption. Okay? All right, so that's it. You got these 8 problems to do. Well, 9 technically because you're doing 2 on this guy right here. Make sure you answer every question. Read the directions fully before you do this thing again. And every chart you need is available to you on that handout. So, but if you need to go to your manual or want to borrow one here in the classroom, you're welcome to do that. But I did give them all to you. You want to print them off, you have my blessing. You want to borrow a highlighter, you have my blessing. Okay? But make sure you pay attention and that you don't blow this thing off. If you blow it off, you're going to be the first candidate to fail. All right, I will shut up and leave you alone then. You're a great audience.